for financial applications and beyond. These findings set the stage for further experimentations where enhancements such as deeper architecture, longer sequence lengths, and additional regulation technique could be explored to optimize performance even further. In this Part 5 enhancement LSTM of a project aimed to push the LSTM model's performance further by incorporating several enhancements. One of the main improvements was increasing the model complexity and adding a third LSTM layer, with each layer containing 64 neurons. These deeper achievements give the network more capacity to learn from the data, allowing it to extract from nuanced features and recognize intricate temporal patterns with an increased number of layers. The model was better equipped to capture relationships that span over longer sequences, enhancing its overall forecasting ability. To provide the model with a richer historical context, I expanded the input sequence length of 20 days. This adjustment allowed the model to consider a broader range of past stock prices when making predictions, which is particularly beneficial for identifying long-term trends and more complex patterns in stock market by analyzing more extensive sequence of past data. The model could better understand how precious market behavior influence future price movement. This change was instrumental in improving the model ability to predict stock prices over a longer horizon, making it more robust in real-world forecasting scenarios. Other crucial changes was increasing the dropout rate of 30%. The dropout is as essential regulation techniques that has prevent overfitting by randomly deactivating a subset of neurons during training, ensuring that the model does not become overly relevant on specific data point. This increased dropout rate helped maintain the model generalization ability even its added complexity. The enhanced LSTM model was trained for 150 approaches with a smaller batch size of 16, enabling more frequent updates to the model weights and biased and following more precise adjustment during the training process. The result demonstrated that the enhanced LSTM outperformed its decreases diseases in terms of predictive accuracy and stability, providing that the deeper architecture combined with proper regulations are critical for achieving high quality forecasts. In this slide performance comparison, to evaluate the performance of the different model, I conducted through comparison of the training and validation loss curves as well as the prediction accuracy. The enhanced LSTM model stood out, the displayed smoother and more stable loss curves, suggesting that it learned more efficiently and generalized better to unseen data. In contrast, the simple RNN and the original LSTM showed fluctuation in their loss curves, indicating challenges in learning and generalizing efficiently. This stability in the enhanced LSTM training and validation loss was strong indicators of this robustness and ability to handle new data without overfitting. The accuracy of the model was also evident in visual comparisons of actual versus predicted stock prices. The enhanced LSTM predictions were closely aligned with the actual stock prices with fewer deviations than the simple RN and the original LSTM. This demonstrated that the enhanced model was able to capture and replicate stock market trends more accurately, showcasing its ability to recognize complex patterns and make reliable forecasts. These results reinforce that the enhanced LSTM capacities for better predictive performance in a financial context, making it is a valuable tool for forecasting stock prices. This performance comparison underscored the importance of increasing model complexity while carefully managing regulations to achieve optimal results. By, by incorporating deeper architecture, expanding sequence lengths, and tuning parameters such as dropout rate, enhanced LSTM outperformed its predecessors. The highlight that well-structured model combined with static regulations and parameter tuning are crucial for high quality forecasting tasks. The findings informed the enhanced LSTM suitability for financial forecasting, demonstrating its potential for real-time application in the financial sector. Throughout this project, I gained valuable insights into strengths and limitations of different neural network architecture. The simple RNN served as a very good starting point for understanding the fundamentals of sequence modeling, allowing me to get a feel how neural uh, network process data in a sequential manner. However, it quietly became evident that the simple RNN had significantly drawbacks, particularly when it came to learning long-term dependencies. The vanishing gradient problem hindered the model's ability to regain information over long sequences, causing it to struggle with tasks that requires an understanding of pattern spanning across a longer term frames. These limitations underscore the need for more sophisticated model capable of addressing these challenges. The LSTM network demonstrated significant improvement by overcoming the simple RNN limitation. The LSTMs use specialized gate input forget output that enables the model to manage memory more efficiently. This allows the network to selectively retain import information and forget irrelevant data, which is essential for capturing both short-term and long-term dependencies. The enhancement ability of the LSTM to learn complex relationships in sequential data made it far more effective for time series forecasting. These reinforce the data that selected the right architecture based on the specific nature and complexity of the task is crucial for achieving optimal performance. Another critical lesson was the importance of regulations and hyperparameter tuning. The enhancement LSTM with its deeper architecture and longer training times demonstrated that the increased complexity could lead to better performance. However, this improvement only occurred when the combined with the effective regulation techniques such as dropout to prevent overfitting, proper tuning of hyperparametry, thus including dropout rates, sequence lengths, and batch sizes, was essential for balancing model complexity and generalization. These lessons will be invaluable for further projects involving neural networks and sequential data, emphasizing the importance of thoughtful architecture design and parameter optimization for success model development. This slide showcases the visual results of the model, focusing on training versus validation loss curves and actual versus predicted stock price plots. These visualizations are vital in accessing each model performance and identifying areas for potential improvement. The enhancement LSTM model stood out due to its smoother and more stable loss curve, indicating better generalization to unseen data compared to the simple RNN and the original LSTM model. This consistency suggests that the enhanced LSTM was able to learn effectively and avoid overfitting, a key factor making reliable predictions on new data. The actual versus predicted price plot were particularly telling on the enhanced LSTM's performance. The model predictions closely align with the actual stock prices with only minimal deviation. These demonstrated that the enhanced LSTM could accurately capture the replicate stock market trends. The reduced prediction error reinforced the model ability to recognize complex temporal patterns, making it is a more efficient tool for forecasting compared to its predecessors. The visual result provides strong evidence of the enhanced LSTM effectiveness in the time series forecasting tasks. These validate the architectural choices such as the addition of an extra LSTM layer and the increased dropout rate, as well as the extended sequence length. The clear alignment between predicted and actual value shows the practical utility of LSTM network for financial forecasting, underscoring their potential in real-world financial application and decision-making. Based on my finding, I have several recommendations for future work to enhance the predictive power and practical applications of the model. Firstly, I suggest incorporating additional features such as trading volumes or open prices. Including these features would provide the model with more context, helping it better understanding market dynamics and leading to more comprehensive and accurate forecasts. By capturing a broader range of market behavior, the model could identify patterns and signals that are not apparent when using only the closing price, improving overall prediction quality. Another critical area for further improvements is hyperparameter tuning. The choice of parameters such as learning rate, batch size, sequential length can significantly impact model performance. Carefully adjusting these parameters and finding the optimal combination can help maximize the model efficiency and accurately. This turning process can be computationally intensively, but is essential for extracting the best performance from the neural network. Moreover, exploring different architectures such as GRU, weighted recurrent units, or attention-based model could provide new insights and possibility enhance the model ability to capture complex relationship in the data. Lastly, deploying these models in real-time application would be valuable. Next step, real-time forecasting system can be implemented to assist analytics and traders in making informed and data-driven decisions. These practical application would showcase the true potential of LSTM and similar models in financial markets, demonstrated their ability to provide timely and actionable insight. These recommendations emphasize the potential for expanding the work done in the project and exploring new possibilities in the real-time forecast. Throughout this project, I gained valuable insights into the strengths and limitations of different neural network architecture, enhancing my understanding of real time series forecasting. The series RNN was a good starting point for learning about sequence modeling and how neural network process over time. However, it struggled with long-term deficiency due to the vanishing gradient problem, limiting its ability to retain important information over long sequences. This shortcome made it clear that a more advanced solution was needed for handling complex time series tasks. This led me to explore the LSTM network, which addresses the simple RNN's limitations with its specialized gates for memory management, enabling it to capture both short-term and long-term dependencies effectively. The enhanced LSTM, deeper architecture, and expanded training time significantly improved predictive accuracy, especially when combined with the regulation techniques like dropout to prevent overfitting, hyperparameter turning, including adjusting the sequential length and batch size was crucial for balancing model complexity with the generalization. These lessons reinforce the importance of choosing the right architecture and optimizing parameter, which will be vital for further projects involving neural networks and sequential data.